In this video, we're going to be using our knowledge of acid ionization in order to calculate the pH of weak acid solutions, such as this solution of acetic acid that we have here. The problem is with weak acids, they do not ionize 100% of the way that a strong acid does. For example, if we consider a solution of HCl, because that solution of acid ionizes 100%, the concentration of a strong acid is equal to the concentration of H3O+ that we make, because the HCl, or 100% of the HCl, loses all of the hydrogen that it has. However, this is not true when it comes to weak acids, meaning this assumption is not something that we can make, because an equilibrium system is formed. However, because an equilibrium system is formed, we can put all of our data into a Rice table and solve the question the way that we would any other equilibrium system, which means that in terms of the algorithm to solve this, you technically already know how to do it. So the only information that we're given is that our initial concentration of acetic acid is 0.50 moles per liter, meaning since we're not told anything else, we can assume that the concentration of H3O+ and our conjugate base is 0 moles per liter, meaning that only the forward reaction will happen, so our equilibrium is going to shift to the products. Since the mole ratio between our reactants and products is 1 to 1 to 1, our change row is going to be -x plus x and plus x, meaning that at equilibrium, our concentrations of each of the reactants and products are 0.5 minus x, x, and x respectively. Now remember that we're calculating pH here, and pH is simply the negative log of the concentration of hydronium, meaning that if we find x using Ka, which is the equilibrium constant for an acid ionization, once we solve for x, we have figured out what the concentration of H3O+ is, and then if we take the negative log of x, we can find what the pH of our solution is. So let's build our Ka expression so that we can actually begin to do our calculations. We know that the concentration of products are going to be concentration of the conjugate base acetate times the concentration of H3O+ divided by the concentration of our acid CH3COOH. And the last thing that we need is the actual numerical value for Ka, which we can find on our Ka data table here, and we can scroll down and find that the Ka for the ionization of acetic acid is 1.8 times 10 to the -5. So let's go ahead and write that in. Now that we have all of the information we need to do the calculation, it's time to actually solve for x. So let's put everything into the formula for Ka and give it solving x a try. So each of the concentration of products is x, so x times x is x squared, divided by the concentration of our reactants, 0.50 minus x, which means that we, in order to get everything into an ax squared plus bx plus c form, we need to multiply both sides of our expression by the denominator here, meaning that we would have x squared is equal to 1.8 times 10 to the -5 times 0.5 minus x, and I'm just going to skip the step where we expand and move everything over to the same side and just go ahead and write that out. So if you do that, we would have x squared plus 1.5 times 10 to the -5x minus 9.0 times 10 to the -6 is equal to 0. Now, if you can factor this by inspection, you can go ahead and do that. Unfortunately, my knowledge of quadratics is not that good, so we're going to take our a, b, and c values and put them into -b plus or minus the square root of b squared minus 4ac2a, also known as our quadratic formula. So -b would be -1.8 times 10 to the -5 plus or minus the square root of 1.8 times 10 to the -5 squared minus 4 A in this case is 1, so I'm not going to bother writing anything here. And C is, of course, negative 9.0 times 10 to the negative 6, all divided by 2, and I'm not going to bother writing 1 here because that's the coefficient for x, because it doesn't change what this number is. Now, the only thing here to keep in mind is remember that we are going to get 2 solutions for x, and one of them is always going to be negative. So this number inside of the square root is going to be a positive number, and if we take a negative number and subtract a positive number from this, we're only going to get a bigger negative number. And since negative concentration is impossible, that one is invalid. So the only valid solution we're going to get is where we add this term under the square root to our initial value. So I'll skip the computation step. You'll just have to put this into your calculator, but you should find that x is approximately equal to 2.9910135 times 10 to the negative 3 moles per liter. Now, if this is x, that means that we have found our concentration of H3O+, which means if we want to solve for pH, we simply need to do the negative log of x, and if we do that, our pH value comes out to approximately 2.52, and if we check significant digits, then we have only 2 significant digits here, which means that we can round this to 2.5. So again, not particularly difficult, although the step where we put everything into the quadratic formula can get a little bit messy. So is there a way that we can shorten this without really compromising the answer that we get? Well, if you remember the assumption regarding percent dissociation that we made back with KSP calculations, if we check the value of Ka, we see that Ka is a very small number, meaning that x is also going to be a very small number here. So an assumption that we can make, because Ka for weak acids and bases is very small, if we assume that the percent ionization, which means the percent of our original acid solution that we have here, is less than 10%, meaning that if less than 10% of our original acid solution ionizes, this means that the x term in here, meaning that the original concentration minus x here, can be ignored. And remember that our percent ionization is equal to the concentration of H3O+, because remember that H3O+ is what is produced when our solution ionizes at equilibrium divided by the original concentration of our acid, so initial. So if this number is less than 10%, we can ignore the x term because we're assuming that this x term is not going to make a significant difference in the original concentration here. So we're going to rewrite this calculation and solve it with this assumption and see whether our pH value changes significantly. So if we write that assumption, so assume percent ionization is less than 10% and therefore ignore x, we would have our Ka value is equal to x squared, and all we would do is write in the original concentration of the acid because we're assuming that this x value is not going to make a significant difference, and this means that our calculations get significantly simpler. So if we take our original concentration and multiply it by the Ka value, we simply get 9.0 times 10 to the negative 6 is equal to x squared, and if we simply take the square root of both sides of our equation, we end up with x being equal to 3.0 times 10 to the negative 3. Now, if we look at this x value with our assumption and compare it to the x value that we get if we put everything into the quadratic formula, we see that they are slightly different, but we see that they are very, very close. 2.991 is effectively equal to 3. And if you take the negative log of x in this case here, you'll find that you actually end up with a pH of 2.52, which is approximately equal to 2.5 as well. And we see that there is no significant difference in the pH of both whether we did the equation using the quadratic formula with no simplification or whether we made this simplification here. And this shows that our assumption of ignoring x because it doesn't make a significant difference works here. In the next video, we're going to look at the same algorithm, but in the solving of pOH of weak base ionizations rather than weak acids.